Support vector machines in machine learning. While many classifiers exist that can classify linearly separable data, such as logistic regression, support vector machines can handle highly nonlinear problems using a kernel trick, which implicitly maps the input vectors to higher dimensional feature spaces. The transformation rearranges the dataset in such a way that it is then linearly solvable. Here we are going to look at how SVM works, learn about kernel functions, hyperparameters, and the pros and the cons of SVM, along with some other real-life applications of SVM. Support vector machines, also known as support vector networks, are a family of extremely powerful models which use method-based learning and can be used in classification and regression problems. They aim at finding decision boundaries that separate observations with differing class memberships. In other words, SVM is a discriminative classifier formally defined by a separating hyperplane. There are several learning models, namely association rules-based, example method-based, deep learning-based, clustering method-based, regression analysis-based, Bayesian method-based, dimensionality reduction-based, instance-based, and a kernel method-based. So let's understand what kernel method-based learning is all about. In simple terms, a kernel is a similarity function, which is led into a machine learning algorithm. It accepts two inputs and suggests the similarity. For example, suppose we want to classify images. The input data is a key value pair, the image and the label. The image data is taken into consideration. Features are computed, and a vector of features are fed into the machine learning algorithm. But in the case of similarity functions, a kernel function can be defined which internally computes the similarity between images and then feeds into the learning algorithm along with the image and the label data. The outcome of this is a classifier. Perception frameworks or support vector machines work with kernels and use vectors only. Here, the machine learning algorithms are expressed as dot products so that kernel functions can be used. Feature vectors generally prefer kernels. Its ease of computing makes it one of the key reasons. Also, feature vectors need more storage space in comparison to dot products. The dot product or inner product of two vectors is the sum of the products of corresponding components. Equivalently, it is the product of their magnitude times the cosine of the angle between them. We can write machine learning algorithms to use dot products and later map them to use kernels. This completely avoids the usage of feature vectors. This allows us to work with high complex, efficient to compute, and yet high-performing kernels effortlessly without really developing multidimensional vectors. Let's understand what kernel functions are. The figure shown below represents 1D function with a simple one-dimensional example. Assume that given points are as follows. It will depict a vertical line and no other vertical lines will separate the dataset. Now if we consider a two-dimensional representation as shown in figure below, there is a hyperplane, an arbitrary line in 2 dimensionals, which separate red and blue points, which can be separated using support vector machines. As we keep increasing dimensional space, the need to be able to separate the data will eventually decrease. This mapping is called kernel function. In case of a growing dimensional space, the computations become more complex and a kernel trick needs to be applied to address these computations cheaply. Support vector machine SVM is a supervised machine learning algorithm which can be used for both classification or regression challenges. However, it is most used in classification problems. In this algorithm, each data is plotted in n-dimensional space, where n is the number of features you have, with the value of each feature being the value of a particular coordinate. After that, we perform classification by locating the hyperplane which differentiates both the classes. Let's create a dataset to understand support vector classification. We use the makeBlob function from scikit-learn. The makeBlobs function can be used to generate blobs of points with a Gaussian distribution. MakeBlobs function also lets you control how many blobs to generate and the number of samples to generate, as well as other host of other properties. So here we generate 500 samples and we make 2 blobs. Then we use a scatter plot to plot the data and we can see the images. We have 500 points and we have 2 blobs. Support vector machine is based on the concept of decision planes that define decision boundaries. A decision plane is one that separates between a set of objects with different class memberships. For example, in the figure mentioned below, there are objects which belong to either class, green or red. The separating line defines a boundary on the right side of which all objects are green and to the left of which all objects are red. Any new object, white circles, fall into the right is labeled, for example, classified as green, or classified as red should it fall to the left of the separating lines. Support vector machines not only draw a line between 2 classes, but consider a region about the line of some given width. Here is an example. We define the x from -1 to 3.5, and we scatter plot the blob samples. Then we have 3 MBD. So we have a line y fit equal m multiply x fit plus b. And we define 3m and 3b. And we have d is the width. So from this graph, we can see we have 3 lines plotted between -1 to 3.5 for the x-axis. And 3 lines are shaded with different widths. Another scenario where it is clear that a full separation of the green and the red objects will require a curve, which is more complex than a line. Classification tasks based on drawing separating lines to distinguish between objects of different class memberships are known as a hyperplane classifiers. Support vector machines are particularly suited to handle such tasks. The figure below shows the basic idea behind support vector machines. Here you will see that the original objects mapped are rearranged using a set of mathematical functions called kernels. This process of rearranging objects is known as a mapping or transformation. You will notice that the right side of the schematic is linearly separable. All we can do is to find an optimal line that will separate red and green objects. The goal of support vector machine is to find the hyperplane which separates these two objects or classes. Let's consider another figure which shows some of the possible hyperplanes which can help in separating or dividing the dataset. It is a choice of the best hyperplane, which is also the goal. The best hyperplane is defined by the extent to which a maximum margin is left for both classes. The margin is the distance between the hyperplane and the closest point in the classification. Let's consider two hyperplanes among all and then check the margins represented by M1 and M2. You will notice that the margin M1 is greater than M2, though the choice of the hyperplane which separates the best one is the new plane between the green and the blue planes. The hyperplane is a line that linearly separates and classifies a set of data. Support vectors are the data points nearest to the hyperplane, the points of a dataset that, if removed, would alter the position of the dividing hyperplane. The distance between the hyperplane and the nearest data point from either set is known as the margin. So from this graph, we know H1 doesn't separate the classes. H2 does, but only with a small margin. H3 separates them with the maximum margin. Let's start with a coding example and import the necessary libraries. Read Wisconsin breast cancer dataset using pandas read_CSV function into an object data from the current directory. After reading the data, we have prepared data as per requirement. Feature scaling is a method used to standardize the range of independent variables or features of data. The min-max scaling or min-max normalization shrinks the range of features such that the range is between 0 and 1, or -1 to 1 if they are negative values. Then we split the scaled data into train, test, split. We can apply SVM after data preprocessing with default hyperparameters. So here we use kernel equal linear kernel. And you can see the default parameters. We can also explicitly set all those parameters when we call svm.svc. Later we will see how to tune those parameters. Then we call the fit function to fit the scaled X-train data and the Y-train data. Then we use the predict function on scaled X test data to get predict Y. We evaluate Y test and the Y predict data. Then we print the accuracy score. The accuracy score is about 0.97, which is good. If we use a Gaussian kernel, kernel equal RBF, we will get the accuracy score which is a 0.935, which is worse than the linear kernel. If we use a polynomial kernel, the kernel equal poly, the accuracy score is even worse. It's a 0.619. How to tune parameters of SVM. In the previous example, the breast cancer example, it's a linear application. So the kernel used linear is the best one. But for more complex application, we can use RBF, which is a radius basis function, or we use a polynomial function. So we should use more advanced kernels to separate classes that are not linear in nature. But for linear application, we should use the linear kernel. In previous breast cancer dataset, we can see the polynomial or Gaussian accuracy score is actually lower than the linear kernels. Using the scikit-learn C parameters and adjusting, we can maintain regularization. C denotes a penalty parameter representing an error or any form of a misclassification. So with a smaller C value, you obtain hyperplane of a small margin, and with a larger C value, hyperplane of larger value is obtained. Lower value of gamma creates a loose fit of the training dataset. On the other hand, a high value of gamma allows the model to get fit more properly. A low value of gamma will only provide consideration to the nearby point for the calculation of a separate plane. However, the high value of gamma will consider all the data points to calculate the final separation line. C is the parameter for the soft margin cost function, which controls the influence of each individual support vector. This process involves trading error penalty for stability. Small c tends to emphasize the margin while ignoring the outliers in the training data, while large C may tend to overfit the training data. Thus, for a very large values, we can cause overfitting of the model, and for a very small value of C, we can cause underfitting. Thus, the value of C must be chosen in such a manner that it generates the unseen data well. So here's the example using kernel as a linear and turning C hyperparameters. We have a C range list from 1 to 26. Then we substitute this range into the kernel, and we get the accurate score for when C is 1 to 26. Let's visualize the above point. From the plot, we can see that the accuracy has been close to 98%, somewhere in between C equal 4 and C equal 5, and then it drops. Here we take a close look at the cross-validation accuracy in the range C from 4 to 5. So we have a list and we arrange C4 to 5, evenly spaced the interval with a 0.2. So there should be totally 5 values, and we compare the accuracy scores for the 5 C values, and then we found that the highest one is a C equal to 4. The gamma parameter is the inverse of the standard deviation of the RBF kernel Gaussian function, which is used as a similarity measure between 2 points. A small gamma value defined a Gaussian function with a large variance. In this case, 2 points can be considered similar even if they are far away from each other. On the other hand, a large gamma value defined a Gaussian function with a small variance, and in this case, 2 points are considered similar just if they are close to each other. In this example, we take a kernel as a Gaussian and turning gamma hyperparameters. So we have 6 from 0.0001, then 0.001, 0.01, and the 0.1, and the 1, and the 10, and the 100 gamma, and we get those accurate scores. And now we plot the gamma for SVM versus the cross-validate accuracy. And we can see when the gamma between 5 and 100, the kernel performs very poorly. The best is gamma is from 0 to 5. Let us take a closer look at the cross-validate accuracy for gamma value in between 0 and 5. The highest cross-validate accuracy for IBF kernel remains constant in between gamma 0.5 and gamma 1. For polynomial kernel, we can also tune in degree hyperparameters. Score is high for second degree polynomial. There is drop in the accuracy score as degree of polynomial increases. Thus, increase in polynomial degree results in high complexity of the model. For the breast cancer dataset, the advantages of SVM is it offers good accuracy. It performs faster prediction compared to naive-based algorithm. SVM is not at all capable of handling text structures. It leads to bad performance as it results in the loss of sequential information, and it is not suitable for large datasets because of its high training time, and it also takes more time in training compared to naive-based. The applications of SVM in real world include face detection, text, and the hypertext categorization, classification of images, bioinformatics, protein fold and remote homology detection, handwriting recognition, and generalized predictive control.